if x and y are independent random variables, then covariance of x y, suppose if x and y are independent random variables, then by definition of covariance of x y, covariance of x y is equal to expected values of x minus mu x into y minus mu y. If x and y are independent, so what will be this expected value? So, suppose if you consider x y continuous random variable, then by definition discrete will be very similar to this. So, this integration will be replaced by summation. So, just we will do it like continuous variable cases, it is minus mu into plus infinity. By definition, this is x minus mu x into y minus mu y, f x y x y dx dy. Now, if x and y are independent random variable, then we know that this probability joint probability density function f of x y can be written as, so then this is minus infinity to plus infinity x minus mu x y minus mu y. So, mu x is the expected values of x and y mu y is the expected values of y. Now, since x y are independent, so this is the joint probability density function, it can be written as product of their marginals dx dy. Since x and y are independent, joint probability density function x y is equal to f x x into f y y. So, that is the reason we can write the joint probability density function as a product of their marginals. So, then this integration, you can see that we can write minus infinity to plus infinity. Suppose first it is with respect to x, we separate out. So, this will be the y minus mu y integration minus infinity to plus infinity x minus mu x f x x, then dx f x x dx f x x dx, then dy. So, now this part, what is this part? So, because x minus mu x f x x dx. So, this can be written as minus mu minus y into this part is nothing but expected values of x minus mu x, and then it will be, because it is a real number. So, it will be outside this integral. So, this is dy. So, we can write, so this part expected value x minus mu x. So, that will be outside this integral. So, because it is a real number, so we can write this is nothing but expected values of x minus mu x, and then the remaining minus infinity to plus infinity y minus mu y dy. Oh, sorry, there is a f y y term, I missed here, f y y dy. So, this will be f y y dy. So, the x minus mu x, so just, so this is nothing but finally what we get, this is equal to expected values of x minus mu x into expected values of y minus mu y. So, that we just wrote it. So, so here we discussed, suppose x and y are, so suppose x y is a bivariate continuous random variable with joint PDF f of x y x y. So, this is actually the assumption here we consider. So, for this computation, so then only we can write. So, if x y are discrete, so if x and y, or we can write let x y be a discrete bivariate random variable with probability mass function p x y x y, or we can write, because it is a discrete value it is taking, that is why notation p x y x y y j. Then also we can show that similarly you can show, basically you can write in this way, expected values of, so covariance of x y, okay, x y be a discrete bivariate random variable with probability mass function x y, and x and y be independent. So, then we know that the joint probability mass function can be represented by their product of their marginal for I is equal to 1 2. So, if it is finite, it is taking finite value, then it will be up to 1 2 up to n, otherwise it may be countably infinite. So, now similarly we can show that covariance of x y, this is nothing but summation of I is x I y j. So, its definition is nothing but expected values of x minus mu x into y minus mu y. So, this is nothing but by definition this is x I y j, x I minus mu x, y j minus mu y, p x y x I y j. So, then similarly we can write x I y j, x I minus mu x, y j minus mu y, and because it can be, because x and y are independent, we can write their product. So, assuming that this summation exists, so then we can write this is nothing but summation of x I minus mu x, p x of x I into summation of y j minus mu y, summation over y j into p y of y j. So, this is nothing but expected values of x minus mu x into y minus mu y. So, both the cases continuous or discrete, both the cases what we are finding that if x and y are independent random variables, then expected values, then covariance of x y, this is expected values of x minus mu x into y minus mu y can be written as expected values of x minus mu x into expected values of y minus mu y. So, what is x minus? So, now what is this? So, expected values of x minus mu x by the properties of the expected values of x minus mu x, but what is mu x? Mu x is a, so it is a, so by properties of the expected values of mu x is a constant, and expected value of x is nothing but, with the notation is mu x is the expected values of x, and it is a constant, again constant, expected values of a constant we have already discussed, this is 0. So, similarly expected values of y minus mu y will be expected values of y minus expected values of mu y, and this is nothing but mu y minus mu y, this is will be equal to 0. So, hence this is 0 into this is 0. So, if x and y are independent random variable, then covariance will be 0. So, but the whether the converse also true, like suppose we have a two random variables, their covariance is 0, can we say that x and y are independent random variables? That is not true always. So, there are many examples. So, expect their covariance are 0, but they may not be independent. So, that is why we can just say that if the covariance is 0, so then we cannot say that x and y are independent. However, if x and y are independent, then we can say that their covariance is 0. So, the correlation coefficient rho it is defined by covariance of xy by the root over of variance of x into variance of y. So, by notation this is sigma y, sigma x, sigma y, where sigma square x is nothing but variance of x we denoted, and sigma square sigma square y is nothing but variance of y. So, in this way correlation coefficient. Now, what is the significance of correlation coefficient? So, how we can have some kind of measure of association between x and y. So, here some information that if they are independent unknown variable, their covariance will be 0. Similarly, correlation also will be 0 if x and y are independent. Correlation coefficient always, because it is a unitless quantity, because this is we are dividing by sigma x, sigma y. So, now it can be shown that by Cauchy-Schwarz inequality, correlation coefficient sigma xy, the correlation coefficient sigma of xy, rho of xy, or we simply denote the correlation coefficient rho xy denoted as rho xy, or simply we denote rho xy or rho xy, defined as rho xy is equal to covariance of xy by root over of variance of x, root over of variance of y. This quantity, just now we have already, this quantity always less than equal to 1, greater than equal to minus 1. This is always lower bound is minus 1, upper bound is 1. Now, there is some significance of the correlation coefficient. If correlation coefficient is close to 1, now if you have some data, like if you make a scatter plot of the data, that means if you plot x versus y, if you see that the data are look like this scatter plot. So, if you have some kind of approximation, some curve, or like how this scatter plot looks like, or if you make a straight line, you can see that this is it looks like it is scattered around a straight line. That means, if x is increasing, y is also increasing in a linear way, this graph. So, y is equal to maybe some a plus bx, some kind of relation, plus some error, because it is not exactly on the straight line. So, this error is very small, so that it is we can see that this is most of the points are close to the straight line. If the scatter plot looks like this, so then this correlation coefficient between x and y will be approximately 1. Now, if we see that the data situated like that, it is also like straight line, but it is the direction will be like if x is increasing, then y is decreasing. So, this is also on the straight line. So, y will be some negative number ax. So, a is a positive number or greater than equal to 0. So, some a minus ax plus c. So, if it is 0, so then it is nothing but y is equal to c, but we want to consider more general cases, a is greater than 0. So, then if it looks like y is equal to minus x plus c, the data plus some error. So, error may be plus minus some values, but error small. So, that all the data looks like very close to the straight line or on the straight line, most of the data. If the data are looks like this, then rho of xy, this will be close to minus 1. However, so basically if you consider the either you can consider rho square or absolute values of the rho. If it is close to 1, so then x and y are related as a straight line. There is a linear relationship between x and y. So, if rho square xy close to 1, then x and y have a linear relationship. Now, if you see that rho value is close to 0, otherwise if rho square x y is close to 0, then there is no relationship, linear relationship. It may be like it is like a circle or some non-linear relationship, like if x is increasing, sometimes y is increasing, sometimes x is increasing, y is decreasing, there is no such relationship like straight line type relationship, then rho square of x y will be 0, correlation coefficient will be close to 0. So, these are the interpretation of the covariance and correlation coefficient that we learned. So, let us discuss one example. So, here also you can see that the covariance of x y denoted by covariance x y, it is defined in this way: sigma x y equal to covariance of x y, expected values of x minus mu x, y minus mu y, that we have already represented. Now, covariance of x y equal to 0, then we say that x and y are uncorrelated. If we see that x and y are uncorrelated, if expected values of x y equal to expected value of x into expected values of y. So, then their covariance is 0. So, then we say that because there is no linear relationship, that is why this is close to 0 if covariance is 0. The correlation coefficient denoted by this, then the correlation coefficient will be close to 0, and then we just discussed that if correlation coefficient is very much close to 0, then there is no linear relationship. So, we say that they are uncorrelated. So, these are the some of the interpretations of the covariance and correlation coefficients. Let us discuss one numerical examples to find the correlation coefficient and covariance. So, consider the binary communication channel. Here it is in this graph, it is given shown below. Let x y be a bivariate random variable where x is the input to the channel. So, x is the input, some kind of switch. If it is 1, then this value is 1. It is 0 if the switch is off, then this value is 0. So, channel, and y is output of the channel. So, depending upon the x values, y has some kind of output. It is like like AND gate or NOR gate or some kind of like if you input something, then there may be some output. So, now x is equal to 0 is 0.5, probability that x is equal to 0, that means it is like a unbiased coin, you are tossing a unbiased coin, and then if it is head, then you on the switch, and if it is tail, then it is if you off the switch. So, then this binary this let us represent it like this. So, this 0 1, x is 0 1, this is the x, and this is the switch, and this is the channel, and but whenever it is 1, so there is a possibility that y can also take 1 or 0, but there is some kind of some possibilities. So, it will not be always 0 or it will be always 1. So, this is the y values, and this is 1 and this is 0 y values, and whenever, so it is given that probability that x is equal to 1 is 0.5, which is equal to probability of x is equal to 0. It is like a unbiased coin you are tossing, that is why both probability 0, both sides same probabilities. Now, whenever x is 0, that means it is off, y can be on also. So, y is equal to 1, probability that y is equal to 1 given x is equal to 0, there is some probability also, this is 0.1, this is 0.1, this is given, and probability that y is equal to 0, y is equal to 0 given y is equal to 0 given x is equal to 1, x is equal to 1, this is 0.2. So, whenever x is on, so there is a possibility that y can be off. So, this probability actually, probability of y is equal to 0 given x is equal to 1. So, this is nothing but 0.2, and this probability that y is equal to 1 given x is equal to 0, this probability is nothing but 0.1, this probability is 0.1. So, these are the information it is provided. Find the joint probability mass function of x y. So, some of the conditional probability mass function it is given, but not all values, we have to find out using the properties of the conditional probability mass function. using the properties of the. So, what are those properties? We know that for any conditional probability mass function, summation if you take of on yj given particular values of xi for fixing xi belongs to the range of x, if you take the sum of this will be equal to 1. So, here if you fix x equal to 0, then what are the possible values of y can take? Y can take 1 or 2. So, then if you take the sum y is equal to 1 given x equal to 0 plus probability that y is equal to another value it can take 0. So, let us write first 0, then for 1 given x is equal to 0. So, see that it has to be fixed, then only you take the sum. So, if you take the opposite, then this property not true. If you take this sum here for xi, so then it will not be 1. So, only whatever the condition it will be fixed because it is a conditional probability mass function, then take the sum of all the possible values condition on xi, then this will be is equal to 1. Now, this value it is provided 0.91, so which implies probability. So, this is nothing but y is equal to 0, probability that y is equal to 0 given x is equal to 0, this will be 1 minus probability of y is equal to 1 given x is equal to 0. So, this is 1 minus this value is provided 0.1, this is nothing but 0.9. Now, from here conditional probability mass function, similarly we will get that. So, if you fix x is equal to 1, so if you take the sum of y value plus y, what are the other value it can take? It can take 1 or 0 we have already mentioned. So, this is also will be 1 because we are fixing this x is equal to 1. So, from here we can get that probability that, so because this probability y equal to 0 x is equal to 1 it is given. So, y equal to 0 x equal to 1 it is given. So, we can find probability y given 1 y equal to 1 given x equal to 1, this is 1 minus probability of y is equal to 0 given x is equal to 1. So, now this probability it is given as probability that y is equal to 0 given x equal to 1, this is given as 0.2. So, this is 1 minus 0.2, this is nothing but 0.8. So, all this probability we know it is required because you want to find finally the joint probability mass function. So, the joint probability mass function, of xy is given by p of xy all the value. So, we have to find all xi yj. So, what are the value it can take, because x can take 0 and 1 and y can take 0 and 1. So, this is we start with 0 0. So, let us start with 0 comma 0, this is nothing but probability x equal to 0 comma y is equal to 0. So, like A intersection B. So, some of the probabilities we know already. So, we know y is equal to 0 x equal to 0, any this probability is known. So, y is equal to 0 x equal to 0, this is known to us. So, given x y equal to 0 given x equal to 0. So, we can write probability it is y is equal to 0 given x is equal to 0 into probability that x is equal to 0. So, because probability of A intersection B can be written as, you know that whenever we are talking about A given B, this is probability of A intersection B by probability of B. Hence, probability of A intersection B can be represented as probability of A given B by into probability. If you forget, that is why I am mentioning it, but several times we have already mentioned it, that this probability of A intersection B can be represented as like probability of A intersection B, it is represented as A given B into probability of B. Now, these probabilities are known to us. Probability of y equal to 0 given x equal to 0, what is that? Y is equal to 0, x equal to 0, it is 0.9. This is 0.9 into probability of x equal to 0, x equal to 0 it is given as a 0.5. So, this is nothing but 0.5, this is 0.45, this is 0.45. So, similarly other probabilities also you can calculate. So, compute. So, let us do that. Suppose we want to find pxy of 0 1, this is nothing but probability x equal to 0, y is equal to 1. So, similarly we will do that, probability that y is equal to 1 given x is equal to 0 into probability of x is equal to 0. So, now probability of y is equal to 1, x equal to 0. So, this y equal to 0, x equal to 1, y probability of y equal to 0, sorry, which probability it is known. So, y is equal to 1 given x equal to 0. So, y is equal to 1 given x equal to 0, it is 0.1. So, this will be nothing but 0.1 into probability of x equal to 0 is 0.5. So, this will be 0.05. Now, we will find out the other probabilities similarly, Pxy of 1 0. This is nothing but probability that x equal to 1 comma y is equal to 0. So, we will find out similarly, this is y is equal to 0 given x is equal to 1 into probability of x is equal to 1. Now, probability of y is equal to 0 given x equal to 1. Y is equal to 0 given x equal to, so this value it is provided to us, y is equal to 0 given x equal to 1 is nothing but 0.2. So, this is nothing but this is equal to 0.2, this is 0.2 multiplication with probability x equal to 1, probability x equal to 1 is nothing but 0.5. So, this is 0.5, 5 into 2 10, so 0.1. Now, the just this is the last probability that x is equal to 1 comma y is equal to 1. Similarly, we will compute, it is nothing but this is equal to y is equal to 1 given x is equal to 1 into probability that x is equal to 1, which is equal to probability of y is equal to 1 given x equal to 1. Here we computed, this is 0.8 into the probability that x equal to 1, x equal to 1 is 0.5. So, this is 0.5, 5 into 8, 40, 40, so 0.4. So, now you can check that if you take sum of all these values, because it is a joint probability mass function, if you take sum of all these values, this should be equal to 1. So, 0.45 plus 0.5, 0.5, 0.1 plus 0.4, 0.5 plus 0.5, this is equal to 1. So, then this is a joint probability mass function we have found. So, this joint probability mass function like you can represent like this. So, suppose this is x, this is y. So, this is 0 1, 0 1. So, then 0 x equal to 0, y equal to 0, this probability is 0.45, 0.45, x is equal to then 1 0, x is equal to 1, y is equal to 0, this is 1 0, this is 0 1, x y 0 1, x equal to 0, y is equal to 1, 0.05. So, this is 0.05 and then x equal to 1, then 1 0, 1 0, x equal to 1, y is equal to 0, 0.1, 0.1 and this is 0.4, x equal to 1, y is equal to 1, this is nothing but 0.4. So, it is actually for clear visibility. So, so we just represent in this way.